In our last lecture, we looked at the frequency response of various RLC circuits and saw that we could get a low pass, a high pass, a band pass, or a band stop filter depending upon the location of the resistor, the capacitor, and the inductor. What we saw in all of the cases, however, is that the maximum gain was 0 dB or a gain of 1. That's because all the circuits we looked at were what we call passive circuits, circuits that only had resistors, capacitors, and inductors. Now we're going to look at an example with an op-amp. An op-amp being an active device means that we can get gains greater than unity or greater than 0 dB. So if you look at this circuit here, it looks like your standard non-inverting amplifier with one addition. It has this capacitor in the feedback path in parallel with the resistor. So we can analyze this circuit using standard op-amp analysis techniques if we use the phasor and impedance concept. So our input Vin, of course, we're going to replace by Vin phasor. And then by virtue of the virtual short circuit approximation, the voltage at this inverting node is also Vin phasor. The capacitor we're going to replace by its equivalent impedance with minus J times 2 times 10 to the 6th all over omega. Now we can do KCL at the inverting terminal. Basically sum up that current plus that current plus that current equals 0. So KCL at the V minus node. Current to the left is Vin minus 0 over 5,000. This current is Vin minus V out, both of those are phasors, over 100,000. And the third current is Vin minus V out over minus J times 2 times 10 to the 6th all over omega. The sum of those three currents equals 0. So let's combine all of the terms that have Vin in them. Vin times 1 over 5,000 plus 1 over 100,000 plus J omega over 2 times 10 to the 6th. That takes care of this term, and this term. That equals V out phasor times 1 over 100,000 plus J omega over 2 times 10 to the 6th. That is this term and this term. And remember, we utilize the fact that 1 over J equals negative J, or 1 over negative J equals positive J. The transfer function h of omega, by definition, is the output phasor over the input phasor. So it's going to equal what? It's going to equal these two together, which is 21 over 100,000 plus J omega over 2 times 10 to the 6th all over 1 over 100,000 plus J omega over 2 times 10 to the 6th. Let's multiply both the numerator and the denominator by 2 times 10 to the 6th. And this now becomes 420 plus J omega over 20 plus J omega. And this becomes our transfer function. Let's look at the magnitude of h for different frequencies. When omega is 0, the magnitude of h is what? It's a magnitude of 420 plus J0 over 20 plus J0, which is just 21, or in dB, 26.44 dB. When omega approaches infinity, what do we get? We get the magnitude of h is equal to what? It's going to be the square root of 420 squared plus some large number squared all over the square root of 20 squared plus some large number squared. What we're going to see is that these two terms swamp out those two terms, and you end up getting that equals 1 or 0 dB. So what we see here is that we get what looks like a low-pass filter that amplifies low frequencies, and at high frequencies it neither amplifies nor attenuates. Sure enough, if you were to look at the frequency response on the next page, we see exactly that. So looking at the Bode plot, we see that sure enough, at low frequencies we get a gain of about 26 dB as predicted on the previous page, and at high frequencies we get a gain of 0 dB or 1. So this is a low-pass filter. However, unlike previous low-pass filters, we actually get a gain greater than 1 at low frequencies. This is because we have an active element or an op-amp. The other difference we see is that the gain at high frequencies is not 0, but it's 1 or 0 dB. If you look back at the circuit here, this makes more sense also if you think of the capacitor as either being an open circuit or a short circuit. At low frequencies, the capacitor is an open circuit. When it's an open circuit, this looks like a standard non-inverting amplifier, and the gain is 1 plus R2 over R1, which in this case was 1 plus 100 kiloohms over 5 kiloohms, or 21. At high frequencies, the capacitor looks like a short circuit, and this looks like a voltage follower. So the gain is equal to 1, which once again agrees with that number there. As a last example, let's revisit the Baxandall tone control circuit. We've seen this Baxandall tone control circuit in earlier lectures. We also saw it in Lab 7. Now we're going to look at it again, but look at the frequency response. So the first thing we're going to see is that our minimum gain is what? Our minimum gain happens when the pot is all the way to the right, so you get that resistance to the right of the pot and all of that resistance to the left of the pot. So the minimum gain is going to be 20 kiloohms over 20 kiloohms plus 100 kiloohms, or 1/6. How about the maximum gain? The maximum gain you get when the pot is all the way to the left, so you get that resistance to the right and that resistance to the left. So the maximum gain is going to be 20 kiloohms plus 100 kiloohms over 20 kiloohms, or 6. So the 1/6 in dB is minus 15.56 dB, and the 6 in dB is going to be plus 15.56 dB. And if you remember how the Baxendale tone control circuit works, we can independently adjust the low frequency gain with that pot and the high frequency gain with that pot. So what we end up getting is the low frequency gain can vary from anywhere from minus 15.56 dB to plus 15.56 dB. And likewise, the high frequency gain can vary from minus 15.56 dB to plus 15.56 dB. We also saw that at middle frequencies, the gain is going to be 1 regardless. So we're going to look at something like that. So what we're going to see is that our total frequency response can be anywhere in this range here. So the pot on the top allows us to change the frequency response in the left half anywhere in that range. And the pot on the bottom allows us to move this frequency response anywhere in this range. So we can, if we want, we can boost both high frequency and low frequencies. We can attenuate both high frequencies and low frequencies, or we can boost one or attenuate the other. Or if we have all the pots in the middle, we can actually get a gain of 0 dB across the whole spectrum, looking something like that. We can actually use multisim to generate a frequency response plot using a function called AC sweep. The first thing you want to do is add voltage probes at both the input and the output. Next thing we do is you select AC sweep here and pick a starting and stopping frequency. I have 10 Hertz and 100 kilohertz. The sweep type, we want decade if we're going to be doing a Bode plot, which we are. The number of points per decade, 100 points is more than enough. And the vertical scale, I like to put at decibel, once again because we're creating a Bode plot. Then you have to go to output and tell Multisim what you want to measure. It defaults to the voltage at probes 1 and 2, but we don't want to plot those individually. We want to plot the ratio of PR2 to PR1. This is the output voltage to the input voltage. So the first thing we're going to do is remove individually these two measurements, and instead we want to add an expression. So we want VPR2 divided by VPR1. And that shows up there. We now save it. Now the first simulation I will run is with both pots all the way to the left. So this top pot is listed as 100%. That means that this wiper blade is all the way to the left. This bottom pot is listed as 0%, which is also all the way to the left. The reason this says 100% and this one says 0% is because the orientation of these two pots is opposite of each other. Anyway, we press the run button and this creates our frequency response plot. I'm not too concerned about the phase plot down here, but let's look at the frequency plot. Notice it starts with the magnitude of about 16 dB, and then it goes down to 0 dB or a gain of 1 at these middle frequencies, and then it jumps back up to 16 dB. If we now move this pot all the way down to there and rerun it, now we're going to get minimum low frequency gain. Notice the high frequency gain is still at 16 dB, but the low frequency gain is all the way down to minus 16 dB. And sure enough, if we now move this pot up to 100%, That's moving this connector all the way down to here. Now we're going to get minimum high frequency gain in addition to minimum low frequency gain. So now they're both at minus 16 dB. So notice that the gain can vary anywhere from minus 16 to plus 16 dB on both the low and high frequency end. And notice the middle frequency is always going to be around 0 dB. And then as a final example, let's move both pots to 50%. At 50%, we expect to have a gain of 1 or 0 dB at all frequencies. So when we run the AC sweep again, sure enough, we get a frequency response magnitude that is flat. Now you might see this upturn at the end, but if you look at these units here, this magnitude is in micro dB. So this is just some rounding error at very high frequencies. For all intents and purposes, we are looking at 0 dB at all frequencies. So in this example, we saw how Multisim can generate the frequency response plots for us for all the different ranges of the two potentiometers. This concludes this packet of notes dealing with frequency response, but because we have plenty of time left, we will actually start the next set of notes dealing with power calculations in sinusoidal steady state. We are now ready to start the last packet of notes in this course, power calculations in sinusoidal steady state, or we could just call this AC power. So in the book, you want to read section 9.1, and there are actually only parts of 9.1 that you need to read. And then you want to read sections 10.1 through 10.6. We're first going to talk about instantaneous versus average power. Then we're going to introduce something called effective or root mean square value of a signal, and that's covered in section 9.1, and then again in section 10.2 and 10.3. We are then going to use the concept of RMS value to calculate the average power in a general AC circuit. That's covered in sections 10.4 and 10.5. And finally, we're going to talk about maximum power transfer, which is covered in section 10.6. This is a topic that we saw much earlier in the semester with DC circuits. We're going to look at it again in AC circuits. These last two topics, complex power and reactive power, we're really not going to get to. We'll talk about them very, very briefly, but we don't really have enough time to finish them this semester. So if you recall, one of the first lectures of EE 210, we talked about calculating the power absorbed by a component in a DC case. So if you had a circuit element here, if you knew the voltage across it, V, and the current through it, I, the absorbed power was just the voltage times the current. The only hard part really in this equation was getting the signs right, remembering when you have a plus, when you have a minus, and then remembering that a plus means absorbed power and a minus means delivered power. That was in the DC case. We're talking about AC circuits now, circuits in sinusoidal steady state. So all the voltages and all the currents are going to be sinusoids. So we're going to see that there are two wrinkles that complicate this power calculation. First off, voltages and currents are no longer constants. They're going to be sinusoids, or in some cases not necessarily even sinusoids. They could be other periodic signals like square waves or triangle waves. The second complication is we see that when you have circuit components that are capacitors or inductors, it causes the current and voltage to not be in phase. So the question is, how will this affect the power? For example, you might have the voltage across a component, looks like that, and the current through a component will be out of phase. Because the voltage and current are not maximum at the same time, could this affect the power? And we're going to see that both of these wrinkles here do affect the equations that we're going to get. So the first thing we need to do is to discuss the differences between what we mean by instantaneous power and what we mean by average power. Instantaneous power is simply the power absorbed or delivered by a circuit element at any instant in time. This is a power equation we've used before. The instantaneous power at time t0 is the voltage across the component at time t0 times the current into the plus terminal of the component at that time t0. The problem with instantaneous power is if your voltages and currents are sinusoidal or any non-constant value, they're constantly changing. And so instantaneous power is often meaningless. So instantaneous power is often meaningless. What's more useful for us is what we call average power, which is the time average power over one period. So imagine that you have a power signal that looks something like that shape. The average power, what you do is you integrate over one period. You integrate over one period the power function and divide by the period. So the average power is 1 over cap t times the integral from some starting point t0 to an ending point t0 plus cap t. And what are we integrating over that period? We're integrating the value of the function. For DC circuits, average power and instantaneous power are the same thing. It's a constant. But for AC circuits, we're going to see that instantaneous power is absolutely meaningless and average power is the power that we are concerned about. So let's now come up with an equation for the average power dissipated in a resistive circuit. So now we have a resistive network with equivalent resistance R, and the voltage across it is V of t, the current through it is I of t. So at this point, we're not restricting the voltage to be DC or AC. It could be a sinusoid, it could be a constant, it could even be a triangular wave shape. But let's see what the average power would be. Average power from the previous page is 1 over the period times the integral from t0 to t0 plus cap t of p of t dt. But power is just voltage times current, and we know that the current through the resistor is the voltage across the resistor divided by the resistance. We can now take that R and bring it outside the integral sign, and we get 1 over R cap t times the integral from t0 to t0 plus tau of v squared t dt. We can then write that as 1 over R times 1 over t times the integral from t0 to t0 plus cap t of v squared t dt. What this part in this bracket is the average of v squared t. But an important point here is this is not the same as 1 over R times the average voltage squared. So once again, this function here is 1 over R times, this would be the average voltage squared. What we have instead is 1 over R times the average of voltage squared. So we get this very important result. The average power does not equal the average voltage squared over R. That's what this is. This is average voltage squared over R. Instead, we get this expression here that we need to look at in more detail. So we're going to introduce a concept called effective or RMS value. So let's assume we have some time varying signal. Doesn't have to be a sinusoid. In this case, it's this triangle wave shape. And it's driving a resistor R. This resistor is going to be dissipating some average power given by this expression here. Let's imagine now a DC source driving that same resistor, and let's assume that we can adjust the source so that these two resistors are absorbing the same power. We're going to define the voltage Vs effective as the DC voltage that gives us the same power being dissipated as this AC signal. So for the circuit on the right, the absorbed power, because it's DC, it's very simple. It's V effective squared over R. So you can sort of think of this V effective value as the DC equivalent of this time varying signal from a power perspective. So once again, let me try to say that again. We're going to find a DC source that causes the same power dissipation in a resistor as a corresponding time varying signal. And we're calling that the effective value. So let's set these two equations equal to each other. So this equation is the average power absorbed when we're driven by time varying signal. This is the average power absorbed driven by an equivalent DC source called V effective. We're going to set those powers equal to each other and solve for V effective, and we get this very important equation right here. V effective is the square root of 1 over cap T times the integral from T naught to T naught plus cap T of V of T squared dt. So some key things. The first thing we're going to do is we're going to square the time varying signal. The second thing we're going to do is to integrate it over one period and divide by the period. In other words, take the average value of it. The third thing we're going to do is take the square root. We call this the root mean square value because we're taking the square root of the average or the mean of the square value. Once again, we're taking the square root of the average of or the mean of the square of the signal. This equation is how you find the DC equivalent from a power generating standpoint of a time varying signal. At this point, this probably seems a little confusing, so we're going to do an example to clarify first off how you calculate it and then how you use that number. Okay, so in this example, we are asked to determine the RMS value of the signal. First thing I should point out is what the average value of the signal here, I'm not calculating it, but the average value is 4/3. So V average is 4/3 of a volt. We're going to see that that number is absolutely meaningless. So let's calculate the RMS or the effective value of the signal. First off, we need an expression for this line segment. This line segment here has an equation 2 plus 2t. Next thing we want to determine is what is the period. The signal repeats every 3 seconds. So the period is 3 seconds. So to calculate the RMS or effective value, what do we need to do? The first thing you do is you square the signal. Then you take its average over one period. So we're going to integrate this. We can integrate it from 0 to 3, or from -1 to 2, or from -2 to 1. We're going to integrate it from -1 to 2. When we integrate from -1 to 2, if you notice, between 1 and 2, this function is actually 0. So we're really only integrating it from -1 to 1. Then to get the average, we divide it by the period. So notice the period is still 3, even though we're only integrating it from -1 to 1. Because technically we are integrating it from -1 to 2, it just so happens that the function is 0 between 1 and 2. So we're going to do that integration. The final thing we want to do is take the square root of it. So notice once again, we're squaring the signal, then we're taking its average value over one period, or its mean, and finally we're taking the square root. So let's do that math. You get the square root of 1/3 times the integral from -1 to 1 of what? 2 plus 2t quantity squared is 4 plus 8t plus 4t squared. When you integrate that, the integral of 4 is 4t, the integral of 8t is 4t squared, the integral of 4t squared is 4/3 t cubed. We need to evaluate that at the upper limit and the lower limit. So that now becomes the square root of 1/3. This function here, evaluated at the upper limit, is what? 4 plus 4 plus 4/3. We subtract that function evaluated at -1. At -1, we get -4 plus 4 minus 4/3. You work out this math, you get the square root of 1/3 times 28/3 minus -4/3. You have to be careful about that double negative there. That equals the square root of 32/9, or 4√2/3 volts. And we use the symbol RMS to indicate that this is an RMS or effective voltage. One thing to note here is that the RMS voltage does not equal the average voltage. Turns out that this number is meaningless from a power perspective. And this number down here is basically the value of a DC source that would yield the same power dissipation as this signal up here. In other words, we're saying that this signal is like a 4√2/3 volt DC source from a power perspective. Once again, the RMS value does not equal the average value, with one exception, except for DC signals. In DC signals, the average value is the RMS value. So why is this RMS value important? Because we can now use this RMS, or effective value, of a time-varying signal to determine the average power absorbed by a resistive load. Turns out that the average power absorbed is just the effective value squared over R, or the RMS value squared over R, or using currents, it's the effective current squared times R, or the RMS current squared times R. In other words, if you replace an AC source by its effective value, you can use the standard DC power equations. So imagine we're given this problem here. We're given the same signal that we looked at in the previous page, and now we're asked to determine the average power absorbed by the resistor. The power absorbed does not equal the average voltage squared divided by R. It'd be nice if it did. That would make our math a lot simpler, but unfortunately, it is not the case. But the power absorbed does equal the RMS voltage squared over R. From the previous page, that was the RMS voltage. You square that, you divide by the resistance, and you get 32 over 81 watts. So in summary then, if you have any periodic signal driving a resistive load, the absorbed power is not the magnitude of the voltage squared divided by R. In other words, we didn't use this 4. It's also not equal to the average of the voltage squared divided by R. Remember, the average of this signal was, 4/3 of a volt. But the absorbed power is this new value, VRMS, or V effective, squared divided by R. So this VRMS is a very, very important measure of any periodic signal because it allows us to easily calculate the power absorbed by a resistor load driven by that source. Now in this example here, our periodic signal was a variation of a triangle wave. In practice, the periodic signal that we use most often is a sinusoid. The good news is all of this work that we had to do in this problem here to find the RMS value of this periodic signal, we do not need to do for sinusoids. We basically need to do it once, and we're going to see that there's a very simple result, and that works for any sinusoidal signal. Turns out that for a sinusoid, whether we're talking about a cosine, a sine, or something in between, the RMS, or effective value, is just the amplitude divided by the square root of 2. It's a very simple result. It doesn't matter what the frequency of the sinusoid is, and it doesn't matter what the phase of the sinusoid is. The RMS value is just the amplitude divided by the square root of 2. So here's the proof. Let's let our function x of t be a cosine omega t plus phi. So at some frequency omega, some phase of phi, some amplitude of a. And we want to calculate its RMS value. So what we do is we first square x of t, then we take its integral over one period and divide it by the period, and then we take the square root. But there's an important trig identity that helps us out here. Cosine squared of x is just 1/2 times 1 plus cosine of 2x. So a squared cosine squared omega t plus phi can be rewritten as this expression here. The a squared can come outside the integral sign. Now we're integrating 1/2 plus 1/2 cosine 2 omega t plus 2 phi dt. This part is just a constant. It integrates to cap t over 2. This part integrates to 0. So why does that evaluate to 0? So cosine of 2 omega t has twice the frequency of cosine omega t. So imagine now a sinusoid, and we're going to integrate this over what amounts now to 2 periods. When we integrate this, over 2 periods, you see that the area is equal to 0. So this whole part integrates to 0. So we now have the square root of a squared times t over 2 cap t. These t's cancel, and we get the square root of a squared over 2, or a over the square root of 2. And we get our final result. The RMS value of a sinusoid, regardless of its frequency, regardless of its phase, is just the amplitude divided by the square root of 2. That means that when you have periodic signals that are not sinusoids, you need to go through the whole process of squaring the signal, finding its mean by integrating it over at one period and dividing it by the period, and then taking the square root. But when you have a sinusoid and you want the RMS value, you don't need to do any of that. You just take its amplitude and divide by the square root of 2. What that means then is when you have an AC circuit driven by a sinusoid, very often when we talk about the amplitude of the sinusoid driving the circuit, we are talking about its RMS voltage. And the way we differentiate between RMS voltage and magnitude or amplitude and peak-to-peak amplitude is by the subscript. So for example, imagine a sinusoid with an amplitude of 1. It has a peak-to-peak amplitude of 2. So the subscript P to P basically means we're measuring it from the largest negative value to the largest positive value. But the third way we can designate it now is just with the subscript RMS. So all three of these things mean the same thing. It means a sinusoid of amplitude 1 volt. But you need to be very careful when looking at a problem to see whether it is listed in amplitude, peak-to-peak amplitude, or RMS value. And once again, with AC signals, a stated voltage or current is often going to be the RMS voltage. For example, your power outlet. You know that the power outlet is 60 hertz, and you probably also know that it's 120 volts. But what does that mean? If you take an oscilloscope and connect it up to the power outlet and measure a sinusoid, are you going to get a sinusoid with an amplitude of 120 volts? No. You're actually going to get a sinusoid of amplitude 169.7 volts because 120 volts is an RMS value. In other words, when we say that that's a 120 volt signal coming out of the power outlet, what we're really saying is that it's the equivalent of a DC voltage of 120 volts. It's actually an AC voltage with an amplitude of 169.7 volts or a peak-to-peak amplitude of 339.4 volts, but we say it has an RMS value of 120 volts, and very often we're very sloppy about saying that it is the RMS value, and we say it's just a 120 volt signal. So bottom line, you need to be very, very careful when dealing with AC signals to make sure you know whether the stated amplitude is its traditional amplitude, peak-to-peak amplitude, or RMS value. Final comment with this is when you're using a voltmeter or an ammeter to measure a voltage or a current in a circuit, when it is set to AC mode, the measured voltage or current is going to be the RMS or effective value. In other words, if you had a signal like this, with an amplitude of 1 volt, and you measure it with a voltmeter, so measure that with a voltmeter, it's going to measure not as 1 volt, but 0.707 volts, because the voltmeter automatically calculates the RMS value, because in essence, it is the RMS value or the effective value of the sinusoid that really means the most, because it's telling us that this AC signal here with an amplitude of 1 volt has the same power generating capabilities as a DC voltage source of 0.707 volts. So at this point, we have tackled one of the two wrinkles dealing with AC power, and that is, how do you handle the fact that your signals are no longer constant? They're going to be time varying. And the way you handle that is you replace the signal by its DC equivalent, or RMS or effective equivalent. And this can work whether you have square waves, triangle waves, or sinusoids. And in the case of sinusoids, it's very simple. The other wrinkle we still have not looked at, and that is, what do you do when the load is not resistive, but a combination of resistors, capacitors, and inductors? And this second wrinkle is what we will look at in next class. Have a good day.